Okay, so we're going to take a look at a very precise definition of a limit. And so in order to do that, we're going to answer this problem, to give us a better understanding. But let's take a look at the definition and see if we might be able to make sense of it. It says, let f of x be defined on an open interval about some number c, except possibly at c itself. So the function is defined, but it may not be defined at c. There might be a hole or something like that on the graph. We say that the limit of f of x as x approaches c is the number L. So the limit is a y value. All right, I'm going to write that down. It's a y value. All right, it says we write it as such. The limit as x approaches c of f of x equals some number L. So it says if for every number epsilon greater than 0, there exists a corresponding number delta greater than 0, such that for all x, the following inequalities are satisfied. The absolute value of x minus c is in between 0 and delta. Then the absolute value of f of x minus the limit L is less than epsilon. What in the world does that mean? It's like I'm talking Greek, and literally I am, because I'm talking about epsilon and delta here. But the definition, the precise definition, maybe it's a little too technical, but we're going to explain anyway with a diagram here. And we've got a really nice example that I think will help you understand this epsilon and delta business. So let me go ahead and I'm going to pull out my highlighters, and I'm going to tell you that what is delta? Well, delta is a tolerance level. It's a tolerance level on x. So I'm going to call that right there one of the deltas, and I'm going to call this one the second delta. All right, and I'm going to note here by writing in delta and delta. So what is it? It's a tolerance level for x. Delta is like how far away can you be from x to have some limit L. Okay, and so epsilon is this part right here, this area here. All right, that's one of the epsilons, and then here's the other corresponding epsilon. Okay, so epsilon is the y value threshold. Okay, so delta is the x threshold, epsilon the y threshold. So here's epsilon, here's epsilon. So the y threshold is numbers that are close to the actual limit L, which is 5. Okay, so those are the epsilons. The deltas, in fact, are thresholds on the x value. So what we're going to do is we're going to take a look at this, and we can solve the inequality. Okay, we can solve the inequality to find the delta value, but from the graph it's pretty easy to see what it is. Okay, they want to know how wide, what is the greatest width that delta can be. And when I say greatest, we really mean the least. It's the one with the least spread. Okay, so in this case it's actually symmetric. All right, but we're going to get into that. So let's go ahead and just take a look. All right, I'm going to say here that this is 0.2. I'm sorry, not 0.2, 0.1. So there's my delta, 0.1, 0.1. I mean, really simply, we can answer it. That's our answer. But we could prove it also with this inequality. So let's take a look. If we are looking for a delta value, we need a delta that satisfies this inequality here. So we're going to figure this out. All right, because we have our f of x, we have our L, and we have our epsilon. And I need to write epsilon here, sorry. All right, now we're going to plug in what we know. F of x is 2x plus 3 minus the limit happened to be 5. I'm reading all of this information here that was given, and it has to be less than epsilon, which is a y tolerance of 0.2. That means that we're going to come in between 4.8 and 5.2 of 5, which is the limit. Okay, so that's what it means. All right, So we're going to solve this absolute value inequality by combining some like terms first. So we're going to go from 3 minus 5 to negative 2. All right. Now, when you're solving an absolute value inequality, this actually becomes compound inequality. It looks like this. Okay. It looks just like that. All right. We solve 2. We solve 2. We add 2 rather to all of the three sides. We get something like 1.8 less than 2x less than 2.2. All right. And then we divide everything by 2. Divide everything by 2. So we get here 0.90 less than x is less than 1.1. So what they're telling us then is if we want to be between 0.2 units of y within the limit, okay, away from the limit anyways, we need to pick x values that are between 0.9 and 1.1. Okay, so this is telling us, hey, if you want the limit to be 5, you're going to have to pick x values that are between 0.9 and 1.1. So that gives us kind of the spread on x that we've got. So what we do is we consider if we're looking for a c value of 1, all right, well, we have to be between 0.9 and 1.1 on the interval. Well, now what you do is you take a look at this spread here and this spread here, and coincidentally they are both the same, but that's not necessary. One could be greater than the other. All right, so the spread there is, I don't know why I keep writing 0.2. The spread is 0.1. I think it's because 1.1 and 0.9 are 0.2 away from each other. But anyways, at any rate, that answers our question that our delta has to be 0.10. All right. So it was pretty apparent from the graph, but we've proved it anyway. So again, we're talking about precise definitions of limits here. You know, maybe it's not the most colorful and exciting thing that you want to learn in a math class, but I think if you have a conceptual understanding of limits, it's a lot better than this. This is very technical, but we're covering it to say we covered it. And if it's not quite understandable, I wouldn't sweat it too much. Understand the concept of limit. That's more important. So, as always, if you liked this video, if you thought this video was helpful, be sure to like and subscribe.